So one note is visible.
Yes, sir.
So this is not restricted just to the Radley-Kwong equation of state, but in general, any cubic equation of state. So let's say a general cubic equation of state. Well, actually, the way I'm writing it's not the general one because I'm using the van der Waals form. But still, pretty much any cubic equation of state you can write in powers of v cube, v square, v and zeroth power. Okay. So what we intend to do is obtain the vapor or liquid like densities from this equation of state, and what is given is pressure and temperature. Okay. So the first determination you need to make is whether the pressure is above or below the saturation pressure. If this is true, then you will get the liquid-like solution. And if this, the bottom one is true, then you will get the vapor-like solution. Okay, so let us see graphically. So once I specify pressure and temperature, all the coefficients of that cubic equation are known to me. Let's say the red denotes the F equal to 0 line. So depending on the pressure and temperature conditions, there are some cases where only one physical route is available, and there are some cases where three physical routes are available. Okay, so for this particular pressure and temperature, three physical routes are available. Okay, the lowest route is the liquid like. Middle route we have discussed is the unphysical route. It dynamic stability condition. And the rightmost route is the vapor like. Okay, so now once you have identified what is the correct route or the equilibrium route, let's say the pressure was above P sat, so that is a separate calculation. So let's say given pressure is above the saturation pressure at this temperature. So therefore I know I will get liquid like route. And now, so rather than hit and trial, what I will say is you will use some numerical scheme for finding routes. For example, let's say I use the Newton method. In this scheme, the initial guess is very important. So what will you take for the initial guess in this case? Remember the van der Waals parameter B, that is an estimate of molecular volume. A was the estimate of intermolecular interactions. B was an estimate of molecular volume. That is roughly the volume of one molecule. So it's clear that the liquid density would be above B. Oh, sorry, the liquid specific volume will be more than B. Okay, the liquid cannot be denser than volume of one molecule. So as an initial guess in this case, I will take V and then I will use the Newton scheme to get to the final answer. Similarly, if the pressure was below P sat, then I will start with the ideal gas volume as my initial guess. Okay, so you can clearly see if I start with the ideal gas volume, I will end up with the vapor like route as my answer. If I start with molecular volume, that means on the extreme left, I will end up with the liquid like volume as my answer. Okay, so that will be the procedure you will follow for any generic cubic equation of state. So is that clear?
Yes, sir.
Any other queries?
In lecture 6,
Mhm.
can you please repeat why the work for adiabatic reversible and irreversible was same? I mean, what's the physical significance of that one? PVT are just state properties, so the numerical values will be same, I guess. But then, how physically we explain that?
I think, okay, so let me first go, which page it is?
Uh, Last page, I guess.
Okay, here, right?
Yes.
All right. So I mean, first question is, or maybe you can explain why this question came to your mind. Why it is not okay if the two works are equal? What is the problem?
The work depends on the path. I mean, PVT are just two points on the graph. So, I mean, how do those points get connected? That is work now. So we can have different graphs, right? Different
Yeah,
paths.
we can
Then
have
work
different
will be
paths.
different. Hmm. So that was only my argument.
No, but if paths are different, even then W can be same. Why?
But
So this was compression or whatever. So have I specified which pressure is greater in the running example? Let's assume it's compression. Okay, so let's go to PV. So state one, state two are fixed. Okay, and it's a compression process. So I go from one to two, and I have two possible paths. One, let's say the reversible path. One, some arbitrary irreversible path. Okay, so let's say green is irreversible. Here I'm not. Anyways, physically, which one would be more accurate? Okay, let's forget about that right now because I'm not sure if there is any constraint on where this other path will lie. But okay, but let's assume there are two different paths, one reversible, one irreversible. And now tell me why the two works cannot be equal. Why you think that? And then I will answer also.
So I'm thinking of work as area under PV curve. So
Perfect. So that's where I wanted you to get to. So is there any restriction on validity of this expression, area under the PV curve? When is this expression valid? Is it always valid, or is there any constraint on the validity of this expression?
okay, am I dropping VDP term?
No, no, no. You're not dropping anything. But if you take a step back, integral will not come. We defined the mechanical work as P external times dV. Okay, and now again think when the boxed expression would be correct for the special case of a
Reversible.
mechanically reversible is sufficient, right? Because mechanically reversible means P external equal to P. All right. So that means, excuse me, the area under the PV curve equal to work is valid only if the process is mechanically reversible. So that means for the irreversible path, the green curve, this is not valid. So therefore, at least mathematically, even with two different paths, you can get the same W. Okay, because area under the curve is valid only for the blue, not the green one. Okay, so that is the mathematical reason. Okay, and now if you go back to how I derived it, so what we were able to do was we were able to relate W. I believe somewhere I must have written this. Okay, maybe I can do that now. So here I've done that indirectly, and maybe in words I have explained it. So this is my starting point, the first law. For the adiabatic process, dq is 0. And therefore, what I get is that the work on change of state from 1 to 2 in this special case is simply the change in internal energy in going from state 1 to state 2. And because internal energy is a state function, state 1 and 2 are same in two different processes. Therefore, without calculation, I could have said that the work done in adiabatic reversible would be equal to adiabatic irreversible if I go from state 1 to state 2. Okay. However, once I come to chapter 5, 6, and 7, we'll discuss physical operation, compression. Okay. So there, what you will see is I will not compare two processes, that is reversible versus irreversible, by saying the initial and the final states are same, but rather, and that is what is basically physically happening in the process. Okay. So in a compression process, the way we compare one compression process against another compression process would be, I will say I have same initial state and I have same final pressure. And now I will compare different compression processes, efficiencies of different compression processes. Because in compression, what is more important is what is the final pressure you are obtaining. Okay. So final temperature is not a design parameter in compression. Typically, lower the value of final temperature, better will be your efficiency, because that would mean less heat got generated. So this I'm comparing adiabatic compression. If you compare isothermal compression, the math will change a little bit. Okay, but in adiabatic compression, a simple measure of your efficiency will be what is the final temperature for the same final pressure. So these three different curves have different levels of irreversibility and therefore different levels of efficiency. That is how I would compare the compression process in practice. That is how compressors are designed. Okay, by asking these questions. Same initial state and same final pressure. Now tell me temperature, that would determine the efficiency. Okay, so in that sense, the part is somewhat hypothetical, that I compare two adiabatic processes, compressive processes, by saying that the initial and final state is same. Okay, so slightly more than what you asked for, but does that explain your query?
Uh, yes, sir. Thank you.
Okay. Any other questions?
So also there was one question about the mercury thermometer, that we cannot measure very high temperatures with it. Is it just
Mm-hmm.
because the tube isn't much longer for mercury to expand, or is there some other
Uh,
reasons as well?
yes, that's part of the reason, but I also mentioned it will be a safety hazard if you try to do that. So of course, don't try to do that. But if you try to do that, it will be a safety hazard also. So why it would be a safety hazard? I believe that was the main part I was asking there in the mercury thermometer question.
Oh, it can break, right? Uh,
But why? So yes, it can break, but why?
The heating increases the pressure. Is it so?
Yes, but by how much? And in which phase it increases more? So there is this propane in the tutorial sheet or the problem sheet. There is a example from a propane plant where something very similar is being asked. Okay, and there you will see that, or you are going to actually you are going to answer essentially what will be the pressure, final pressure, depending on the initial state. Okay, so I don't know if anyone has read that problem, but if you read through it, it's a vapor liquid coexisting initial state, and depending on how much vapor you have in the initial state, for the same final temperature, you can get very different final pressures. Okay, and that question is essentially asking you to quantify. Okay, if I start with 20% vapor, what is the final pressure? If I start with 10% vapor, what is the final pressure? If I start with 5% final 5% vapor, what is the final pressure for the same final temperature? So that's what that question is asking. And same argument is applicable for the mercury thermometer also. The problem there is you are trying to heat a liquid in a closed vessel. So when you heat a liquid in a closed vessel, the increase in temperature is much, or sorry, the increase in pressure is much more significant than if you were trying to heat a gas in a closed vessel. In both cases, the pressure will increase, but the pressure will increase much more significantly if you have a liquid in a closed vessel. So that argument is valid for mercury thermometer. That argument is valid for the propane plant accident that I have mentioned in the problem sheet. Okay. Any other questions? Okay. So from my side, I will just discuss a little bit about solving that propane container problem. Problem number, if anyone can help, what is the problem number? 3.44, and then there's some subparts which I have given. Okay. So here we'll try to visualize first what is happening. And many times when solving these problems, it's good to first draw the process on a PV curve. And because the problem involves us starting in the coexistence region, I am also drawing the binodal BCD. Okay. So we are given that the initial temperature is 43 degrees Celsius and pressure is 16 bar. And there are three different initial states. %20 vapor, 10%, and 5%. So these are the three initial states. Also, the final pressure is given to us. So final temperature is given to us. So let us draw the isotherm at that final temperature. So T equal to 70 degrees Celsius, that is given. All right. And now in each of these cases, the process that has happened is constant volume heating. The starting point is either 5%, 10%, or 20% vapor. At coexistence conditions corresponding to 43 degrees Celsius. So that is the data given to us. All right. And now what we are interested in knowing is if final temperature is 70 degrees Celsius, what is the final pressure? So how should I go about solving this? Constant volume process. So can you try to solve it on the graph first? If you can solve it on the graph, you would be able to solve it quantitatively also. So what are the solutions on the graph? Too much lack of morning energy. So what should I do on this graph to get the solutions?
We can take vertical projections to from red points to black line, right? Can we?
Perfect. Yeah. So I will take vertical intersection points. Okay, what color you want? Okay, let's do green. So it's slightly off scale. So my vertical is slightly horizontal. So if you do the calculation, starting at 20% up at the saturation point, and if you take other two projections, you will end up at much higher pressures. So here you can already see what is happening. Can anyone point out what has happened? Look at the slope of the black line in different regions. And then tell me what is the problem if you heat a liquid in a closed vessel.
phase 2?
No, no.
Pressure increases very rapidly. I mean, we are doubling the concentration, but the pressure changes.
So if I look at isothermal compressibility, for example, and I can do that comparison of liquid versus gas. I don't, which symbol have I used for isothermal compressibility, beta or kappa? Okay, let's for now put it without symbol.
Uh,
Kappa has been used.
Isothermal compressibility.
Thank you. So when I say liquids are almost incompressible, okay, we are saying that kappa T is very small. Or sorry, okay, done it the other way now. Change in volume with pressure. Yeah, okay. So if I'm saying kappa T is very small, essentially what I'm saying here is for a small change in density, you would require a very large change in pressure. Okay, that is the meaning of saying that liquids have negligible compressibility. Okay, and that's what you're seeing on this graph. The high slope of that black line in the liquid region is essentially saying that for very small changes in V, you need very large changes in P. Okay, so kappa T in the liquid region is very, very small, implying essentially a vertical slope. Okay, that's what uh, graphically it means. Okay, so now all the data is given in the problem. I will give you the answers for the three different cases. So the way you will do is in the initial state, calculate V. Okay, so for that you need Vt, the tank volume. So V is specific volume, Vt is the tank volume that is given to you, and you need the total mass in the beginning. To get the total mass in the beginning, you find out the volume occupied by the vapor in the beginning. That's why that 20%, 10%, 5% is required. Since temperature is given, it is given you are at coexistence. You can find out the saturation volume or calculate it by one of the correlations. Similarly, find out the mass of liquid. Okay, so the first term is mass of vapor in the vessel. Second term is mass of liquid in the vessel. And from this, you can calculate specific volume. Okay, so this V at these three different conditions, which was 20%, 10%, and 5%. And this I'm giving you in centimeter cube per mole, comes out to be 119. At 10%, 106, and at 5%, 101. So these are the three values I get. Now I know that in the final state I have, or actually that's also I need to find out what is the phase. So that's the first question. what is the phase, all right? So T final is given to you 70 degrees Celsius. So add this T final. To find out the phase, you need to find out whether the specific volume is below VL-sat, between VL-sat and VB-sat, or above VB-sat. Okay. So at 70 degrees Celsius, these two volumes I can calculate. The liquid volume is 109. And the vapor volume is 805. Okay. So now I can populate the other part, which is I can also find out phase in the final state. Because volume I know. So if the volume was 119.07, then what will be the phase in the final state? Given the conditions at TF, 70 degrees Celsius, the two volumes are given to you. So what is the phase in the final state at 20%? %33 chance of success, three possibilities. Either subcooled liquid, coexistence, or superheated vapor. Those are the three possible answers. So what is the correct answer?
Coexistence.
And why?
Between 109 805, it lies between 109 and 805.
Perfect. So since the volume is between these two numbers, that means both vapor and liquid need to be present. And from here, you can calculate how much of these two. Okay, so I'm not going to that part. And on the other two cases, now you can see by the same logic, because now the volume is below VL-sat. In both cases, you have a subcooled liquid. So now the next part is pressure. What is the pressure in the final state? Okay, so first part, what is the pressure? Because it's coexistence, find out the saturation temperature, saturation pressure at 70 degrees Celsius. The answer comes out to be 26 bar. For the other two cases, you will need to use the equation of state, subcooled liquid. So now for these two cases, I will need the subcooled liquid PVT data. And the way I will need to solve it is, I am given V and T. I will need to find P. So that is how I will solve the equation of state in this case. Given two variables, in this case, those two variables are V and T. I will need to find P. So you will do the calculation yourself. The answers come out to be 30 bar and 60 bar. Okay, so you can see, depending on the initial space you are leaving, 20%, 10%, or 5%, you can get very different final pressures. Now it depends what is the limit. Okay, so that design question still you have to ask, can my vessel sustain 30 bars? Can my vessel sustain 60 bars? And what is the expectation? How much heat input you expect, so that I know what is the final temperature that can go. So all of those questions you still need to ask, but once you have answers to those questions, you can then design your vessel, design your process. So vessel design will tell you what is the maximum pressure you can sustain. External conditions will tell you what is the temperature you can expect. And basis of that, you will decide how much vapor space you need to leave in your vessel. Okay. So that was the only question today I wanted to discuss. Other was already asked, which was to how to solve the equation of state. So those were the two questions I wanted to answer. Rest I will take up in the tutorial. If there are any other questions, I can take them up now. Okay, so we'll close the session.